Yes, welcome everybody. It's our pleasure, or my pleasure and our pleasure today to welcome Pascal van Hentenrik. Before you, Pascal, can go on, please let me introduce you. Pascal is at the H. Milton Stewart School of Industrial and Systems Engineering at Georgia Tech in Atlanta. And before he was a professor for computer science at Brown University. And before that, I guess he was leader of the optimization group, which was a pretty large group, as I just read today, at the National ICT in Australia. And he was Seth Bonder Collegiate Professor of Engineering at the University of Michigan. So he's also a honorary professor at the Australian National University. And besides many, many prizes that I will not mention because otherwise Pascal will never start with his talk, he's fellow of the Association for the Advancement of Artificial Intelligence and, for instance, Informs. He was, as I just said, awarded many other prizes. And his research focus is on artificial intelligence, data science, and operations research, with applications mainly in mobility, energy systems, resilience, and this is what he is also talking about today, privacy. So I also just checked his Google Scholar profile today, and this is really remarkable, so please let me mention this. It counts, I guess, more than 22,000 citations, and then I scroll down and down and down, so there are more than 600 publications. So Pascal, at least one can say that you're not the lazy guy. So we're even more proud that you find the time today to speak in our seminar. The floor is yours.
Thank you, Martin, for the nice introduction. I just have good collaborators and good students, right? So, I'm going to talk about differential privacy of hierarchical census data, and in particular an optimization approach, which is which you will see that the relationship between that differential privacy and optimization is, I think, a very fruitful direction, and we have been applying to various problems in energy and mobility as well. But this is really going to be about census data, which is a very hot topic right now. So this is based on a couple of papers with a number of collaborators, especially Nando, who is assistant professor of computer science at Syracuse, and Keiyu Zhu, who is one of my PhD students. And so mostly the talk is going to be on the first paper, but I'll touch upon two topics at the end on the second and the third papers, because there are some very interesting issues, social issues that are linked to differential privacy. And I want to talk a little bit about them at the end. So this is what I'm going to talk about in the talk. I'm going to start with some motivation. Talk briefly about differential privacy. I assume that everybody has heard about it, at least at some level. And then I'll define the problem. And then I talked about the optimization problems that we need to solve. And I give you part one and part two. So part one is going to be a simplified version. Part two is the real problem. And then I'll discuss about the experimental results. And then I'll talk about bias and variance in differential privacy and also fairness. That's what I'm going to talk about today. So please feel free to interrupt at any time if you have any questions, obviously. So what are we trying to do? So we are trying to release data about people, right? So we are imagining that we have a database containing a lot of information about various people in a given country, and we are interested in finding various statistics about these people. For instance, you know, how many people live in a particular household and earn less than $50,000. So we submit a query to the database and we get an answer, right? Now, typically we want to do that not for one particular country, but also for various regional granularities, right? So in the United States, you would talk about counties, and the counties are part of a state, and the state is part of the entire country. And so we want to report statistics at the level of the counties, and then at the level of the state, and then at the level of the country. I'm sure you have the same thing in Germany with the lands and so on, right? So this is what we want to report: statistic at different levels. So we have a hierarchy of different regions, and we want to report the same statistics at these different granularities. Now, the census data in the United States, for instance, is used for many, many different things. So, for instance, for allocating budgets in education, schools, or in this particular case, which is really relevant, how you actually how much vaccine do you actually distribute in the different states. They're also used for finding out if you need to put, for instance, ballots for the elections in a particular language, which is not English, for instance, Spanish. And so these census data is very important for many of these decisions, which have, fundamental societal impact, as I will discuss later on. One of the things that you need to do also, at least in the United States, I think Europe has even stronger rules, is that when you are releasing data, you cannot release identifiable information about people. And this is Title 13 in the United States. So you have to release this data, but you have to preserve the privacy on every individual in the data set. And that puts some constraints, interesting constraints on how you need to do that. And you may know that it's not sufficient. Obviously, those of you working in differential privacy know that it's not sufficient just to anonymize the data, because you have these linkage attacks. So if I release a data set, for instance, Netflix released a data set of ratings of movies, you can actually link that to another data set where you have also information of these users. And by combining the two, you can actually identify people. And that was demonstrated nicely by one of the papers showing the power of these linkage attacks. Okay, and there are many examples of that where when you combine two different data sets, you can actually identify persons uniquely. So you have to have a framework which is robust enough to prevent these linkage attacks. It's not just sufficient to anonymize the data. So one of the framework to do that, which is very robust to this, to a lot of different attacks and in privacy linkage attacks, is differential privacy. And what differential privacy does, at a very high level, is that you get the answer to your query, and then you put some noise that will, not only anonymize, but preserve these kinds of linkage attacks. So you basically guarantee privacy by adding noise to your data. So that's the very high level. I'm going to, formalize this in a moment. But informally speaking, the key concept of differential privacy is that you want the answer to two queries on very similar database to be the same. So if you have one database and another database which is the same except for one individual, you want the queries to be essentially the same. And I'm going to, tell you formally what that means. So obviously what we are designing is, randomized algorithm, because we are putting noise, right? So and the noise is going to depend on when you execute the query. And so we have this randomized mechanism that are giving you answers on this database. And what you want is that the probability of getting a specific answer on a database and on a similar database where you have one more or one fewer individual is going to be essentially the same. So they are linked by this epsilon value that you see here, one, exponential of epsilon, which is really 1 plus epsilon if you want. And so this basically tells you that these two answers cannot differ too much. So I'm going to illustrate that with some pictures because this is easier to understand. So you have two databases, D1 and D2. So you can put a query on them, and then you get these probability distributions for the answers because you have a randomized mechanism. Now you add one per person, you get a different answer. And what you really want is to bound the difference between these two answers at any point for any kind of answers that you can get. So that's what differential privacy does. So you cannot really distinguish between these two databases, and therefore you protect the privacy of every one of the individual. Another way to think about this is that you have plausible deniability. We don't know if the individual is inside the database or not. Right, so this is what we can do. And the way you can achieve differential privacy is typically by adding this calibrated noise that I mentioned before. That's the simplest way to do it, but that's the only thing that we will need today because most of the things that we are going to do is going to take place afterwards. So in a sense, what we do is that we have this query that we ask, we get the answer, and then we put this calibrated noise that I will describe in a moment. So you don't get the exact answer, you get this random, this randomized answer, which has some calibrated noise. Now, this noise typically depends on the sensitivity of your query. And this is a notion that I need to define. But once again, what you have is you have two databases and they differ by one individual data point. And you are trying to see what is the maximum difference that you can get when you ask a query for these two databases which differ by one individual. And that's the query sensitivity. In a sense that the worst case difference that the query can have. And we'll talk about that in the context of the census data later on. And so once you have this sensitivity, you can actually generate the noise, calibrate the noise such that it depends on that sensitivities and depends on the privacy level that you want. So if you have a very, if you have a very strict sensitivity like 0.001, obviously you will have to put a lot of noise. If the sensitivity is large, obviously you put more noise. Right? And so this is what is happening. So what I'm showing you here is the Laplace distribution, which is one of the most ubiquitous mechanisms to introduce noise in differential privacy. Now, the other things that you can do is use a double geometric mechanism. That's what we're going to use today because we have discrete data. And therefore, this is also a, kind of a symmetric distribution around 0. And, it's defined in essentially the same way as what you have seen before. And once again, it depends on the privacy level that you want and the sensitivity of the query. So we can put the noise that particular way. Now, let me talk about hierarchical data release because this is what we want to do today. So once again, I told you we want to release data at the level of the county, at the level of the states, and at the level of the country as a whole. And so to do that, you will see pictures like this, right? So this is my hierarchy. So you see the US at the top, you see 2 states here. I'm simplifying, obviously. Georgia and New York, and these are 2 counties in Georgia. These are 2 counties in New York. If you follow the election last year in the US, you probably have heard about these 2 counties. Fulton is the county where Atlanta is located. One other thing which is interesting here is that in gray, you see the various counts. Okay, so these are the numbers that the actual numbers. And the blue counts there are the noisy count. This is what we are releasing as the result of the query, but no, it's privacy preserving. We have applied differential privacy on that. And you can immediately see that there are some interesting issues, right? So now we have the value 2, which is close to 3. We have the value 7, which is reasonably close to 5. But when you add them together, you get 9. But the number that you generate for Georgia is 6. So you have a difference between the sum of these 2 numbers and the numbers that you have there. And that's not supposed to happen, of course. So you have to kind of reconsider this consistency. So once you generate data on this hierarchy, there are 2 things that are happening. Some of the counts are going to become negative. If the number is small and you add, you subtract, noise, which is too large, you're going to get a negative number, which doesn't make sense, right? So it's like a negative number of people. And then you have these inconsistencies between the sum of let's say, the people living in the counties and the people living in the states. So you have to reconcile those. So how do you actually put the noise such that you satisfy the constraints that you need in this hierarchy and also the constraints on the meaning of these counts? And so that's what we want to deal with. And so what we're going to do is use a really nice property of differential privacy, my favorite property of differential privacy, which is post-processing immunity. So one of the things that you can do in differential privacy is to make sure that you can apply, once you have a differentially private output, you can apply any function to it, and you will preserve the differential privacy guarantees. Obviously, you don't have to look at the real data when you're doing that. So strictly speaking, if you have a mechanism which is epsilon differentially private, and you apply this function from the output to anything, the result is going to still be epsilon differentially private, which is very nice. All right.
Pascal,
so yeah.
Pascal, what happens when I take the inverse?
So the inverse of this transformation?
Yeah, of M. As G, then it cannot be differential private anymore. Otherwise, I wouldn't have started with the project. Right?
No. So M is a randomized mechanism, right? And it's guaranteed to be differentially private. If you apply G to it, you will. So there is a theorem that says that you will keep the differential privacy. Basically, what it means, Martin, is that you cannot invert this. Okay. You cannot recover the real data from this, right? Okay. Okay. And so the only thing that you can do interesting things on it, but it will not change fundamentally the differential privacy properties. It will not change them at all, right? So you're going to get another output. It may have properties that you want, but you will still not be able to, identify an individual is there on that, right? That's the key point. Okay. Thanks. And so this is very important, right? So it allows us to do anything we want on the output of a differentially private mechanism. Okay. And so in this particular case, what we want to do is to say, hey, one of the things that I want to do is that the counts that I'm releasing, the noisy counts that I'm releasing for Cobb County and Fulton County has to be exactly equal to the count for Georgia. So I have a noisy count for Georgia, I have a noisy count for Cobb, I have a noisy count for Fulton, but now I want to post-process them such that the sum of the two counties is going to be equal to the sum of the state of Georgia, right? And I also want to make sure that the counts are positive. That's what I want. So I want to restore the feasibility of these counts and also satisfy all the constraints, all the hierarchical constraints that I have. Now, so how can you do this? You can do this optimally by using an optimization problem. And this is the optimization problem that you need to solve. So I have my noisy counts. Okay, so these are the counts that I have as the results of the differentially private mechanism. And what I'm interested in doing is, getting this post-process count. Okay, so I'm going to post-process the count such that they are as close as possible in using this L2 norm to the noisy counts, but no, they satisfy these hierarchical constraints, and they are, for instance, also strictly positive, right? Or non-negative. All right, so that's what we need to do. We need to solve this optimization problem, and now we are as close as possible to the noisy counts, but now we have meaningful data that we can release. The sum of the counties is going to be equal to the state, and so on and so forth at every level of the hierarchy, right? So I can apply the noise, solve this optimization problem, and now I have noisy counts that satisfy all the constraints of my problem. Okay, and so we have applied these kinds of mechanism to a lot of problems in mobility, in energy, where you have physical constraints and so on. Here, the constraints are just the non-negativity constraints and the hierarchical constraints. Okay, so now we have to solve this problem. And the key idea here is that we have to make it scalable, right? So when you look at this problem, it's a convex problem, but we are going to have to solve it for very, very large data set, right? So in the US, we are talking about 300 million people. If you do that at the scale of Germany, it's probably like 65 million people or something, right? So we have to scale at that level. So it has to be extremely fast, and you have to scale it. So how are we going to do that? So we're going to use dynamic programming instead of solving this problem directly. Also, when I say it's convex except that the counts are integer. So it becomes the constraints are convex, but the counts are making it non-convex, obviously. So it's a very difficult problem to solve. So how do we do this? We do this using dynamic programming. So what we're going to do is have two phases. One is a bottom phases where we compute optimal cost tables for every one of the region. So for every one of the regions and every one of the value, we are going to compute what is the optimal cost for that particular region and all the descendants of that particular region. And then in the top-down phase, we are going to use this table to find the optimal solution at the root, and then find the values that you need to get for every one of the counties and then every one of the states and so on at every level of the hierarchy. Right? So that's what we're going to do. And I'm going to go into the details of this. So this is the optimal cost at the node R. So this is a particular node in the hierarchy that I've shown you. And we are looking at, what is the optimal cost if I assign the value V, to that particular node. And obviously you have two parts. The first part is the L2 norm for that particular value. So this is the noisy count that I got. This is the value V that I'm trying to choose. And I'm computing the L2 norms. And then I have to find the cost of all the descendant of that particular region. Okay, I have to find the optimal allocations of those counts, the post-process count for all the descendant. But as I told you, this is a dynamic program, so we know the table for every one of the children. Therefore, we can only look at the children. And therefore, we use the optimal table for the children, find a post-process count for every one of these children, such that we minimize this expression, but we also satisfy the hierarchical constraint. So at every one of the level of the hierarchy, we can construct these tables, and they give us a way to know what are the various optimal costs for every one of the possible values. Okay, when you arrive at the top, you can find the one which is the minimal cost, and then you can propagate that down using the top-down phase. All right. So in a sense, what you can see here is that you're looking at the optimal cost for the US. These are the possible value for the US. These are the cost table for New York, for Georgia. And then I'm computing this cost table for the US. And the cost table can take the value 1, 2, 3, 4, and so on and so forth. And for the value 0, I have the difference between this and the noisy count. The noisy count here is 2, so I have 4, and then I have to add 9 and 0, so the cost here is 13. If I take the value 1 for the US, now I have two possibilities. I can take 4 and 0, I can take 9 and 1, I can take the smallest of these two, and then I have the cost for the L2 norm, which is 1 here. And therefore here I would have a cost of 5, and so on. You do that for these tables. Okay, so that's what you do. You solve this optimization now at every one of the regions instead of globally. And then you have this bottom-up phase and this top-down phase. Now, I haven't told you how I solve this optimization problem here, right? So I still have at every one of the node an optimization problem to solve, which in a sense link this value V with the values that I can choose for every one of the children, right? And using the cost table for the children. But the beauty here is that you can prove that these cost functions are convex piecewise linear. So you see some examples of these here. So this is Georgia, this is based on the counties, this is the US, and so on. And because of that, you can solve this optimization problem by just merging this table using, a nice sorting algorithm. And so basically you need n log n time where, n is the number of values that you need to consider for every one of the regions. And therefore you have a very efficient algorithm for solving the optimization problem at every one of the nodes. And since you are doing one bottom up and one top down phase, this is going to be overall an extremely efficient algorithm. Okay, so we'll see that. I'll show you the result later on. All right, so that's what we have done. Now, so far, what I have done is simplifying the problems, because the problem that we need to solve is actually a little bit more complicated than this. And so I'm going to define for you the problem, but typically what you want is not releasing a single value. You typically want to release what is called group sizes queries. And so this was defined by the Census Bureau, by some of my colleagues here in the US who have worked on these particular problems, that particular problem. And I'm going to define it intuitively in the next couple of slides. Okay, so this is the group size data, and you have to look at the table here on the left. So these are all individuals. And then you have this unit. And the way to think about this unit is where they live, right? A is an address, B is an address, C is an address, and so on. So these units are where people live. And then obviously these addresses are in a county, in a region, and so on and so forth, right? So we have the hierarchy afterwards. And the quantity here, we have all ones here because we're going to count people, but if you count the number of cars, that would be the number of cars that this particular person owns, and so on and so forth, right? So that's what we have there. And so once you have this table giving you the data, what you can do is to actually count the number of people living at a particular address, right? So you get 3 living in A, 1 person living at B, 1 person living at C. That's for Georgia. In New York, it's a little bit more interesting. There is one location where there are 3 people, another location where there is 1 person, another location where there are 2 people. And what you're interested in the census data problem in the US is releasing this group size. How many group of size 3? How many groups of size 1? And so on. And that's what you see here. So you see that in Georgia, there are 2 groups of size 1. These are the 2, and 1 group of size 3. And in New York, you have 1 group of size 1, 1 group of size 2, and 1 group of size 3. So that's what you are releasing, all right? So it's a little bit more complicated, not much, but a little bit more complicated. So this is once again, when you see the hierarchy, instead of releasing 1 number, you are releasing a set of numbers there, two groups of size 1, 1 group of size 3, and this is one of each for New York City. And then at the next level, obviously, you sum them, and you get the number of groups for that particular state, in this particular for the US. Okay, so that's what you have. Now you have a little bit more constraints here. You have to make sure that, not only the sums here are, making sense. So 2 + 1 = 3, but you also need to make sure that the number of groups is actually being preserved everywhere. And so I need a little bit more notation to define the optimization problem. And so what you will have now is the noisy count. That's the count returned by the differential privacy mechanism for a particular region and a particular size. And then I will compute the post-process count for the same region and the same group size. And so this becomes the optimization problem. And it's essentially the same as before, except that now I have these L2 norms on the vectors. I still have the hierarchical constraints, but now I have these additional constraints, which is actually making sure that the number of groups is the right number of groups. So we'll have to restore also the fact that the groups are going to be the same. And so that can be done in a very nice fashion by transforming the problem. So instead of looking at the overall post-processing the way I've shown you, you basically split the problem into group sizes. And so you basically have the hierarchy for group of size 1, hierarchy of group of size 2, size 3, size 4, and so on. And then you have one more level where you basically say, hey, the number of groups here has to sum, has to be equal to the, the overall number of groups. And therefore, you can transform this problem, which is more complicated, to the problems that I've shown you before. And this is nice. Okay? No, so that's how we can do it. So it's essentially the same technique. It's a little bit more complicated because the hierarchy is bigger, but it's the same technique that we can apply. Okay, now I need to talk a little bit about the sensitivities, right? So because we need to add the right amount of noise. And so what you can see here is that the various groups there, and you see the various counts for every one of these groups. And so you can wonder now, if I'm adding one individual or removing one individual, what's going to happen? So if I remove an individual from this group of size 2, what's going to happen is that I'm going to decrease this number by 1. And then the group is going to become a group of size 1. So I'm going to increase that group by 1. And so the sensitivity of the query here is going to be 2. There are 2 values here that have been changed. And therefore, the L2 norm is going to be equal to 2. Okay? Now, same thing if I'm adding a person in a group 1. That group 1 is going to become a group 2. So I'm decreasing this one by 1, increasing the other one by 1. So my sensitivity is going to be equal to 2. Okay? Now, can we do better? And so there is this idea in histogram queries and other queries to use cumulative counts. Or instead of reasoning really about the counts, you can reason about cumulative counts, which means what? If you look at this value 1 there, is going to be the sum of these 2 counts. So it's basically the sum of all the counts up to 1. This is the sum of all the counts up to 2. So 4, 3, and 2, giving you 9. Okay? So why do we want to use these cumulative counts? We want to use them because now you're going to see that the sensitivity is better, right? So if I'm removing one person from a group 2, I'm going to decrease a group 2, but I'm going to increase a group 1. So I'm changing the group 1, but I'm not changing this value there because, when you sum all the group from 0 to 2, you still have the same number. And this is very nice because now the sensitivity is 1, so I can decrease the noise that I need to add by a factor of 2. Okay, and same thing when you add a person. If you add a person of group 1, this is becoming a group. This is decreasing, but the number of group of size 0, 1, and 2 is going to stay the same. So once again, you have a sensitivity of 1, which is nice. I can decrease the noise that I'm introducing by a factor of 2. Okay, now. So the problem is that, so I want to use this cumulative count, but the problem is when you use this cumulative counts, what you get is that you have to make sure that when you restore feasibility, in addition to having the hierarchy constraints, you also need these constraints that make sure that these counts are non-decreasing, right? So they are cumulative, okay? And so that's a problem because now this problem is more complicated, right? So you have to deal with this. And this is breaking this basically beautiful convex piecewise linear nature of the cost table. And so we are stuck. So we don't know how to do this. So what are we going to do? So one of the things that we could do is to say, hey, I'm going to put the noise using the cumulative counts. And then I'm going to extract the real counts by using this very tiny optimization that I can do for every one of the regions, just restoring the feasibility of the cumulative counts, then getting the real counts, and then I'm using the algorithm that I've shown you before. And this is a pretty good algorithm, okay? But it's not optimal. It's not the optimal algorithm on the cumulative counts, and we are optimizers, so we really want the optimal solution. Okay, so how can we do that? Okay, how can we use cumulative counts and at the same time we actually get the optimal solution for that optimization problem? And the key idea is extremely simple when you think of it. It's basically flattening the entire hierarchy using a post-order traversal of the tree. So we take the hierarchy and we transform it into a long chain. And so what you see there is you start from a node A1. So that's a post-order traversal of the tree. We're going to use A1, A2, then go up and then go down, go to the brothers and sister of that node, go up, go down, go down, go up. And then at some point you go up again. And then you could go to the brother and sisters and keep doing that, the siblings. Okay. So you basically flatten this entire hierarchy into one single chain. And then the constraints between them are of two types. They can be smaller or equal, because this is the cumulative counts. But when you go up, this is the last node in that particular, this particular group. You basically, this particular set of children. Then you go up, and obviously there the cumulative count has to be the same as the count of this particular node. And then once again you have a smaller equal there, smaller equal equal, smaller equal, smaller equal equal, and so on. And that's how you're going to define the optimization problem. So your optimization problem is only one level now. You're still minimizing the L2 norms of the counts and the difference between the noisy count and the post-process count. But now you have two constraints, either these inequalities between the adjacent, the prior count and the count you are considering now. And that can be either an inequality or an equation, depending on whether they are at the same level, right? So once again, this is the optimization problem that we can solve, and we can solve it by dynamic programming. Why? Because now the optimization problems for every one of these nodes is extremely simple. It's once again the minimization of the L2 norms plus what is happening to the previous node, but there is only one node now. You don't have a set of children. You have only one node, which is the predecessor. And if the node is at a different level, so you use the same value. Otherwise, you have to solve this optimization problem here, which is choosing the best value for the previous node. But this is very simple because you are just looking at one node and the set of possible value for that node. So this is linear in the set of values that every one of these nodes can take. So we can compute this whole thing in essentially a dynamic program where the time for every node is linear time. So really, really very low computation time. Okay, so very nice. So you're going to see the experimental result now. I'm going to give you 3 data sets. The first one is the census data. It has about 300 million individuals there, about 1,000 different groups, and the number of leaves is about 7,500. The second one is taxi data from New York City. It has about 24 million, 3 groups as well. So very different data set. And then we're going to use a synthetic data set to show you scalability by limiting the number of group size. So you cut this data set by cutting the number of group size. And that obviously cut the size of the hierarchy and the length of the chain. And these are the results. And you're going to, so this is a logarithmic scale. So you see very, very different orders of magnitude speed up. So MC and MH are when you are actually using the real optimization problem, the problems that I've shown you at the beginning, where you have integers and then these convex constraints. So they don't scale very well. This is the top-down algorithm, which is an approximate algorithm used by the Census Bureau for some of the tests that they have made for releasing the census data last year. These are the optimization algorithm, the DP there are the optimization algorithm that I've shown you, where you solve the optimization problem using the tables, and this is the approximation using the cumulative counts. So you don't see much difference between them. These two ones are actually relaxing the integrality constraints, and you see that they behave very well. So that's when you are actually solving the optimization problems, but not taking into account the integrality constraints and rounding at the end. And this is the algorithm, the last algorithm that I've shown you. As you can see, it's orders of magnitude more efficient than any of the other ones. Okay, so we really have a very highly scalable algorithm here for solving this census data. Let me show you that on the real data. So this is the real data set again, logarithmic scales here, and you can see that the algorithm here, this is on the census data, this is on the taxi data, is taking orders of magnitude fewer, less time than the other algorithm, including the one that the Census Bureau has been using, and some of the optimization algorithms that are pure optimization algorithm there, based on the dynamic programs and the pure optimization algorithm. You also see that this is true for every one of the differential privacy levels. And this is kind of remarkable, right? The time that it takes for things that have 300 million individuals. This is the accuracy. And once again, what is interesting to see here is that the algorithm using the chain is as precise, almost as precise, or sometimes, or more precise than any of the other algorithm, which means that you have a really nice trade-off between really efficient computation times and roughly the same or better accuracy compared to the real data counts compared to the existing algorithm. So that's essentially the algorithm that I wanted to present to you. Let me just check the time here. Okay, so let me go now to two additional issues that I want to talk about. And this is bias and then fairness. Now, one of the things that we know is that the Laplace mechanism or the geometrical mechanism that I've shown you are unbiased, right? So if I generate enough data, the expectation of the noisy count is going to be exactly the count. But so one of the issues that we need to investigate is what is the effect of post-processing on this expectation, right? Are we introducing bias? How are we modifying the variance? And so these are experimental results on the census data. And once again, so you see the residual, the difference between the expectation of the noise and the real data counts. And you see that with the Laplace mechanism, it's this very nice unbiased distribution. But once we do the post-processing, you see bias, significant bias being introduced. And so one of the things that we wanted to do is that where does this come from? Does this come from, which constraint is responsible for this, right? And so, we started trying to understand that for various classes of problems where we use the Laplace mechanism to generate the noise, and then we have a set of equation that we need to satisfy. And so the results here are what we are trying to do is to see, hey, what is the bias when we are putting the non-negativity constraints and when we are not putting the non-negativity constraints and when we are putting the non-negativity constraints. And the rest is essentially the same post-processing algorithm that you have seen so far, except that the constraints are a little bit simpler. And so one of the results which is very interesting here is that all the bias is coming from the non-negativity constraints. If I have only equations or a set of equations, I'm not introducing any bias. And in fact, what I'm doing is that I'm actually reducing the variance. So if you have a dimension of the problem, for instance, the number of counties is small, you will reduce the variance substantially. If the number of groups is large, then essentially you converge to the Laplace distribution. And so this is very interesting. On this particular problem, adding the new constraints and restoring feasibility of these new constraints is not actually changing bias and is reducing the variance. But on the other hand, if you have these non-negativity constraints, you introduce bias. You also reduce the variance in general, but you introduce biases. And so this is the variance reduction and the convergence that you can see for the problems that I've just shown you when we have no negativity constraints. And you can see, you know, as the number of counties, for instance, is increasing, you can see that we are converging towards the Laplace distribution. So now I want to introduce the final thing, which is this fairness problem. And so you may have heard, you know, this is very, very recent. So you have heard that there is a lawsuit going on in the United States between the state of Alabama and the Census Bureau. And so they are essentially trying to prevent the Census Bureau to use differential privacy. And this is very interesting. So you can read all this online. So this is the docket for the file. And this is from the transcript that you can read. I mean, this appeared, I think, in the last couple of days. And so the judge is actually asking a very good question. He's asking the defendant, are there the plaintiff? They are asking, is there any privacy loss budget setting that would be acceptable? So I find this remarkable, right? So you have a judge asking a differentially private question. And the plaintiff is saying, I'm skeptical that they would be. And this is a very interesting answer, because if you take epsilon infinity, you can release the real data. So obviously there is. And so that the point of the judge wanted to show that there is nothing capricious in what the Census Bureau was doing. And so, but still, this raises an issue. People can start asking, when we actually put differential privacy on a data set, how does it affect decisions that can be taken using that data? And this is one of the things that we wanted to investigate, right? So if you have the sensitive data, you apply differential privacy, you have privacy preserved data, but now people are going to start using it for various different things. Some of the things that I mentioned at the beginning. For instance, they can decide the budget allocated to schools, whether you are actually putting a ballot in Spanish in a particular county or not, right? And so the point is that, you know, what is happening to these problems? Is this fair? You know, what is differential privacy doing to this? So this is, for instance, Title I for elementary and secondary education. And what you can see is that these are grants that are above, you know, distributing about $6.5 billion. And the way you do this is proportionally. So you count the number of children who needs these grants, and you divide that proportionally by everybody, every one of the various regions. And you have a weight factor which depends on the cost of living, for instance. Okay, so this is what we need to do. And so if we actually use differential privacy data, what is happening when you do something like this? And what you see on this plot, this is experimental results on the census data, is that you see that there will be biases, obviously. So this is the biases is, once again, the difference between the expectation of the allocation and the real allocation that you would have if you allocate, if you use the real data. So this is the real data, and this is the expected allocation done by differential privacy. And one of the things that you see there is that some schools are going to get a lot more money, and other schools are going to get fewer money. And this is in thousands of dollars. So this is 100K, this is $45,000. So you see significant differences here depending upon your level of privacy. And so that's an issue, right? So, and one of the things that we are now trying to do is to say, hey, for different kind of mechanism, how much bias do you have, and are you fair or are you not fair? And we define the definition of fairness if for everyone, which is getting some particular budget, the bias is the same. And we call something alpha fair if the difference, the bias is bounded by this value alpha. So nobody is getting the difference between two different allocations is not going to be more than alpha. And so you can start having some good results and some bad results. So this is a positive result that tells you that if the Hessian of every one of these allocation rules is constant, then the problem is going to be fair, alpha fair. There will be an alpha such that it's alpha fair. That alpha can be big, but at least it exists. And so that's a positive result. But obviously, when you look at the allocation of this budget for education, this function, this Hessian, is not constant at all, right? And that's why we have this experimental result that's showing you that there is a bias in the allocation, and the allocation is inherently unfair in this particular case. So what are we going to do? So can we solve this? And so that's one of the things that we are currently investigating. But I can show you one of the things that you can do very naturally. So, and this is something that we have done in a lot of release of differentially private data. So what we can do is not only release this xi privately, but we also can take this sum and release that sum in a privacy preserving manner. So you have a little bit of a cost of privacy when you're doing that, but it's a small cost. And once you do that, this particular allocation rule becomes linear, and therefore is going to be alpha fair for some alpha. And so when you do that, look at the results are very interesting now because you are not introducing any bias, and you're also very accurate as essentially the Laplace mechanism, which is in some sense optimal, right? And so this is very nice. So you can actually linearize this rule by having this redundant release and making sure that things are consistent, and what you get is basically fair allocation in this particular case, and you preserve the accuracy of the allocations. So in conclusion, what I want to tell you is that so we have looked at challenges in census data release, and I've shown you that we can actually accommodate all the hierarchical constraints and non-negative count, and we can do that at large scale. And the key idea is doing a combination of flattening this entire hierarchy and using dynamic programming, solving these optimal cost tables at every one of the nodes. So really this chain-based dynamic programming over cumulative count is highly accurate and highly scalable. And you can solve these problems in, essentially, what is it? It would be linear in the size of the number of regions and the set of values that every one of these regions can take. I also talked a little bit about the bias and the variance in post-processing. Typically, post-processing is going to reduce variance, but it can also introduce bias due to the non-negativity constraints. Once again, there are techniques to try to avoid this. I have no time to talk about them, but we'll describe them in a coming paper. And then fairness is also a very important issue. You have to make sure that how you're going to use this census data is done in a fair fashion. And once again, I give you some definition of what fairness can do, positive and negative results, and some mitigation approach that we can take. Now, all of this is just the tip of the iceberg. I think we are starting to look at differential privacy and what it does to different decision-making problems in a more holistic way. And I think this is going to be a very fruitful area for a lot of research in the next couple of years. And obviously, I will be very happy to take any question at this point. So thank you very much.